Chapter 23 Introductory Electronics. Hello everyone, Dennis here. This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me. In this lesson, here are a few topics that we are going to learn. The first is Thermionic emission. We will learn how thermionic emission happens, followed by the application of thermionic emission, which is cathode ray oscilloscope (CRO). Then we also learn a few electronic components such as potential divider, light-dependent resistor (LDR), thermistor, diode, capacitor, and resistors and color codes. You might find that some of the topics here have been discussed in the previous lessons. The reason is because at first this course O-level physics is designed based on the subject code of 6091, and I get some requests to have more contents like this chapter, which covers the topics of O-level physics subject code 5054. There are a few more topics need to be covered here. So if you found the topics are repeated, just take it as revision. Alright, so let's start the lesson. Thermionic emission. The very first question you ask is, what is thermionic emission? Thermionic emission is the emission of electrons from a metal surface when a metal is heated to a high temperature. The word therm means thermal energy or heat. Ionic means ions or charged molecules. When a metal is heated, the electrons within the metal gain enough kinetic energy to escape from the inward pull of the positive nuclei at the surface. The number of electrons emitted from the surface increases with the increase of temperature of the metal. The metal filament where electrons are emitted is called cathode. So cathode will be the negative terminal. The emitted electrons are called cathode rays. In the next section, we are going to study the structure of thermionic diode, so later you'll see the whole picture clearer. Let's study the structure of thermionic diode. First, we start with a glass bulb. Inside the glass bulb is vacuum. At this end of the glass bulb is filament, where this filament is connected to an AC voltage supply at about 6.3 volts. Hence, this filament is heated and cloud of electrons is formed around filament, where this cloud of electrons is invisible. Now, this filament is cathode or the negative terminal. At the another end of the glass bulb, we place a metal plate and we make it to be positive terminal or anode. So now, since this metal plate is positive terminal, it accelerates electrons and cathode ray is formed. This cathode ray is made out of a lot of electrons. Then we connect this metal plate to electroscope. And now this electroscope is negatively charged. What we can observe is deflection between plates is observed because same charges repel. Next, negatively charged rod is placed near electroscope and greater deflection between plates is observed. This shows that the charges emitted by thermionic emission is negative. Conventional current and electron flow. In the previous lesson, we have discussed about conventional current. In conventional current, positive charges flow from positive terminal to negative terminal of a source. So this diagram explains how conventional current flow. So this is the positive terminal and this is the negative terminal of the source. The source is connected to the load. The current flows out from the positive terminal of the source, flows into the load, and then go out from the load, flows back towards the negative terminal of the source. On the other hand, the direction of electron flows. So let's look at this Thermionic diode, where this is the filament connected to an AC supply and forms electron clouds. Another end of the glass bulb is the metal plates, and we connect anode supply, which is high voltage DC supply, to this Thermionic diode. So metal plate is connected to the positive terminal of the anode supply, hence it becomes anode. So it attracts the electrons and the electron accelerates towards the metal plate, hence electron beams form. So here is the electron flow. It flows out from the negative terminal of the anode supply towards the filament, and then the electron beams touches the metal plate and the electrons flows back to the positive terminal of the anode supply. So the filament is the cathode or the negative terminal. Comparing these two diagrams, electrons flow from negative terminal to positive terminal of a source. Electron flows in opposite direction of conventional current. We can modify the Thermionic diode for better use. And here is how we can modify the Thermionic diode. We start with a glass bulb, and one end of the glass bulb is filament connected to an AC supply of 6.3 volts. And then we connect the circuit with a high voltage of DC supply of 2.4 kilovolts. So this part will be the metal cylinder, which is anode with a hole in the center. So here is the electron clouds, which is cathode. The electrons are accelerated and form electron beams and hit the surface of another end of the glass bulb. So the another end of the glass bulb is painted with zinc sulfate coating so that bright green spot can be seen when the electron beam hits the round surface of the glass bulb. Next, let's discuss how we can change the direction of electron beams. The electron beam's direction can be changed by electric field. So let's look at this diagram. This is two metal plates. The top metal plate is positive plate and the bottom metal plate is negative plate. So when cathode ray passes through these metal plates, it will be deflected towards the positive plates and then continue to move in a straight line. This is because cathode rays deflect towards positive terminal of electric field, because cathode rays consist of a lot of electrons. Electrons are negative, so they will attract towards the positive plates. Electron beams direction can also be deflected by magnetic field. Now let's see how magnetic field affects the direction of electron beams. So from this diagram, the circle and the cross symbol is the magnetic field pointing towards the paper. And this cathode ray passes through this magnetic field. The direction of deflection of cathode rays passing through magnetic field can be determined with Fleming's left-hand rule. We have learned Fleming's left-hand rule in the previous chapter. So let's see how it works. First, point your index finger from North Pole to South Pole. So for this case, it's towards the paper. And then your middle finger points to the left, which shows the conventional current, because cathode ray is the direction of the electron flows. Hence, conventional current will be in the opposite direction. You realize that your thumb points downwards. So the thumb points to the direction of the deflection. If you you follow the Fleming's left hand rule properly, your left hand will be like this. Okay, so for this case, the cathode ray will bend downwards. Application of thermionic emission. There are two popular applications of thermionic emission, which are cathode ray oscilloscope (CRO) and television tube. So here is how CRO look like, where we can use CRO to measure the waveform of a voltage. So this is the television tube. Actually, it is an old version of television, where you can see that the old version of television is very bulky. The reason is because if you open the casing of this television, we'll see it is something like this, and actually it applies thermionic emission concept. Now let's discuss cathode ray oscilloscope and how it works. Structure of CRO and how to interpret its screen have been discussed in chapter 22. But over here, I will repeat it again. If you have watched chapter 22 lesson, you can treat it as a revision. Alright, so just a brief revision here. So this is the structure of CRO. The basic concept is the electrons emitted from the indirectly heated cathode are attracted and accelerated towards positive cylinder, which is the anode. When the accelerated electrons hit the fluorescent screen, kinetic energy of electrons are converted into heat and light energy on the fluorescent screen. Now, let's discuss the important parts of a CRO. We start with the filament. Filament is heated by low AC supply. Electrons are emitted due to thermionic emission. Next, the grid. The negatively charged grid makes the emitted electrons into a beam. It controls the number of electrons reaching the screen. Then, anode. Anode is positively charged. It is used to accelerate the electrons. Next, X-plate. X-plate deflects electron beams horizontally, followed by the Y-plate. Y-plate deflects electron beams vertically. If both X-plate and Y-plate function together, the electron beams will oscillate in waveform manner. So this table shows how X-plate and Y-plate influence the trace on the screen. If both X-plate and Y-plate are turned off, we'll see a dot on the screen. If X-plate is turned on while the Y-plate is turned off, we'll see a horizontal line on the screen. If the X-plate is turned off while the Y-plate is turned on, we'll see a vertical line on the screen. If both X-plate and Y-plates are turned on, we'll see waveform on the screen. Next, the fluorescent screen. Fluorescent screen is coated with fluorescent material, which is zinc sulfate. Electron beams will glow when hit the screen. This is how images are shown on the screen. Taking reading from CRO. Let's discuss the uses of CRO. CRO is used to display waveform of the voltage that we are measuring. It also is used to measure AC voltage and to measure short interval of time, can be in milliseconds range. Now, here is the looks of the panel. We have the grid or the screen, which shows the waveform, and there is a connector connect to the probe, where this probe will probe on the point that we want to measure. So there is a knob which is for the Y gain in the unit of volt per division. So here we have 1, 2, 3, and 4, 5. Another knob is for the time base in milliseconds per division. Also have 1, 2, 3, 4, 5. Okay, so for this case, in the Y gain, it is pointed at 2, means it is 2 volts per division. For the time base, it is 2 milliseconds per division. So this is one division for the horizontal axis and the vertical axis. From this waveform, the dotted line shows the neutral position of the waveform, and we can measure the amplitude. So the measurement is the number of division times selected scale. So for the amplitude is the number of vertical division times the Y gain scale. So for this case, it is 2 division for the amplitude multiplied with the Y gain scale, which is 2 volts per division, and the value of this amplitude is 4 volts. Now, this is the measurement for periods. For the period, it is the number of horizontal division multiplied with the time-based scale. So we have 4 divisions multiplied with 2 milliseconds per division, which gives us the period of 8 milliseconds. And from here, we can calculate the frequency, where it is 1 over the period t. So the value is 1 over 8 times 10 to the power of negative 3, which is 125 Hertz. In this section, we discuss about electronic components. There are a few electronic components to learn. The first is potential divider, followed by light dependent resistor LDR, then thermistor, diode, capacitor, and finally resistors and color codes. There are two types of electronic components, which is passive electronic components and active electronic components. So what is passive electronic components? Passive electronic components are electronic components that consume, dissipate, or store energy but do not produce energy. They do not have the ability to produce gain, which means to increase the power or amplitude of a signal. They do not have the ability to control electronic current by means of another electrical signal. They do not have the directionality, that is, they operate in the same way regardless of the direction of the current flowing through them. So here is a diagram illustrate directionality. For this case, both resistors R1 and R2 operate the same, although the currents are flowing at different directions. Here are a few examples of passive electronic components, which are resistors, capacitors, inductors, and transformers. Next, what is active electronic components? Active electronic components are electronic components that produce energy and gain. They have the ability to control the flow of electricity, and they have the directionality. That is, they can only operate in the correct direction of current flowing through them. Here are a few examples of active electronic components. The first is all types of power supplies, like battery, DC supply, AC supply, and electric generators. All types of diodes, for example, PN junction diodes, light emitted diodes, LEDs, Zener diodes, Schottky diodes, unipolar or bipolar diodes. All types of transistors such as bipolar junction transistors BJT, field effect transistors FET, junction field effect transistors JFET, metal oxide semiconductor FET, MOSFET. Integrated circuits IC. Examples are digital circuits, analog circuits, processors, ball grid array or BGA packages, power ICs, half-effect sensors, and current sensors. The first electronic component that we want to discuss is potential divider. Here is the circuit of a potential divider. In the previous chapter, we know that the formula for V1 is R1 over R1 plus R2 times Vin. For V2, it is equal to R2 over R1 plus R2 times Vin. Potential divider is used to vary the potential difference of the load according to the requirement in the circuit. Here are a few examples. The first one is rheostat. The sliding contact of the rheostat is adjusted to control the fraction of the total potential difference. The popular application for rheostat are volume of a speaker and fan speed controller. Another example of potential divider is light-dependent resistor LDR, which is used to detect the brightness of the surrounding, hence control the brightness of light bulb. One more example of potential divider is thermistor, where it is used to detect surrounding temperature, hence control the temperature. Here are a few examples of thermistor, which is water heater, air conditioner, refrigerator, and fire alarm. Now, the first application for potential divider is the rheostat or potentiometer. So this is a rheostat which you can find in the physics lab. And this is the circuit of the rheostat, where we have the sliding contact to control the resistor, hence we can control the Vout, where the Vout formula is the length of BC over the length of AC times Vin. Because remember that the resistance is directly proportional to the length of the resistor. So you can find a rheostat in our daily life. For example, this is the volume controller, where this part there are a few sliding type rheostat, and the bottom one is the knob type rheostat. Also, another example is the fan speed controller, where you can control the speed of the fan by adjusting the knob. Another application of potential divider is LDR, which is light dependent resistor. And here is the symbol of LDR. First, it looks like a fixed resistor, but it has arrows pointing at the resistor. So the arrows represents the light around the resistor. The resistance of LDR changes with the light intensity from the surrounding. Resistance increases when light intensity decreases. So please remember this. Resistance increases when light intensity decreases. The resistance decreases when light intensity increases. Right, so here is a potential divider with the LDR is placed at the first resistor, and this table will illustrate how it works. So if the light intensity around it is low, the resistance of LDR is high, and the current is low. Hence, the light bulb dims or turn off. If the light intensity is high, the resistance of LDR is low, and the current is high. Hence, the light bulb shines or turn on. Next application of potential divider is thermistor. This is the symbol of thermistor. Resistance of thermistor changes with temperature. And please remember, resistance increases when temperature decreases. On the other hand, resistance decreases when temperature increases. So this is the potential divider where the thermistor is located in the first resistor. And this table illustrates how it works. If the temperature around the circuit is low, the resistance of the thermistor is high. Hence the current is low and the light bulb dims or turns off. If the temperature is high, then the resistance of the thermistor is low. So the current will be high and the light bulb will shine or turn on. The next electronic components that we want to discuss is diodes. The most common type of diodes is the PN junction diode. This is the symbol of PN junction diode, where this is the anode of the diode and this is the cathode of the diode. In physical product of diode, it will look like this. There is a stripe and one side of the diode which represents the cathode and another end is the anode. Diodes conduct electric current in one direction only. A very common application of diode is the rectifier, where we have discussed it in chapter 22, but I will revise again in this chapter. PN junction diode is made up of two semiconductor regions, which is P-type region and N-type region. In between P-type region and N-type region is a neutral junction. So here's to illustrate how it looks like. We have the P-type region and the N-type region. In between these two regions is the neutral junction. N-type region contains significant number of free electrons that then holes, which means positive charge. For P-type region, it contains a significant number of holes, which is positive charge, then free electrons. Enough energy needs to be supplied to overcome the barrier supply in the neutral junction so that current can flow through it. There are two types of biases in a diode, which are forward bias and reverse bias. For forward bias, when the P-type region is connected to the positive terminal and the N-type region is connected to negative terminal of a battery. So here's how it looks like. So this is the diode with the positive terminal and the negative terminal connected to the proper terminals of a battery. Then the diode has enough energy to overcome barrier potential in the neutral junction, hence current can flow through it. So here is the current flowing out from the positive terminal of the battery and then go towards the positive terminal of the diode and then come up from the negative terminal of the diode. Then turn on the light bulb and flows back to the negative terminal of the battery. So this is forward bias. So the diode is forward bias and the forward bias voltage is 0.7 volts for silicon and 0.3 volts for germanium. The second type of bias is reverse bias. When the P-type region is connected to the negative terminal and N-type region is connected to positive terminal of a battery, and this is how it looks like. The diode is reverse biased and its resistance becomes very high. Hence the current cannot flow through it and the light bulb will not turn on. Let's revise again rectification. Rectification is a process of converting alternate current AC to direct current DC. There are two types of rectification, which is the half-wave rectification and full-wave rectification. So The first one is the halfway rectification, and this is how the circuit looks like. So the current will flow through the diodes. So diode only allows the current to flow in one direction. And this is how the waveform looks like. And so we have V in and V out. So when the V in is in the positive cycle, the V out will follow. When the V in is in the negative cycle, then the V out will be 0. Then repeat the same process. The V in is in the positive cycle again. The V out will follow. Negative cycle of the input, the V out becomes 0. Next, let's discuss full wave rectification. And here is the circuit. First, the input voltage is connected into 4 diodes, which are connected in this manner. At these 2 points, it is connected to a load, and we connect a voltmeter parallel with the load to measure the output voltage. So here's how the waveform looks like when the input voltage is in the positive cycle. So the current will flow through in this direction. First, pass through these diodes, and then follow through the load at this point and flow back to the input voltage. Hence, the output voltage will follow the input voltage. Next, when the input voltage is in the negative cycle, then here is how the current flows. First, it will flow through these diodes and then pass through the load at the same point as the positive cycle, and then pass through this diode and flow back into the input voltage. Hence, the output voltage will follow, but is in the positive cycle again. Now, the process repeats again when the input voltage goes back to the positive cycle, where the current will flow in this direction again into the load and returns back to the input voltage, and hence the output voltage will follow with the positive cycle. Similarly, when the input voltage goes back to the negative cycle, the current will flow into this direction, into the load, and flows back to the input voltage, and the output voltage waveform will follow with the positive cycle. Next, let's discuss light emitting diode LED. So here is the symbol of LED. You can see that it is exactly the same as the PN junction diode, but with 2 arrows pointing outwards. These 2 arrows represents light is emitted from LED. This is the physical look of the LED, with one leg is longer than another leg. The shorter leg is the cathode and the longer leg is the anode. And when you take a closer look of the head of this LED, we can see that there are 2 flags. One is inverted flag. Alright, so again, the long leg is the anode, the shorter leg is the cathode. LED has exact same function as PN junction diode, where it is to conduct electric current in one direction only. There is another additional feature for LED where it emits light when current flows through it. IV curve of PN junction diode. The IV characteristics of a PN junction diode can be described in this graph. So for the x-axis, it is the voltage V, and the y-axis is the current in milliampere. So this is the fault bias region, where when the voltage increases gradually, the current also will increase gradually until it hits the fault bias voltage. Then the current increases drastically. At the negative side of the voltage, we'll have this reverse bias region where the current is very close to zero until at one point it breaks down, and this region is called the breakdown region. The next component that we want to discuss is the capacitor. A capacitor is an electronic component that is used to store charges. Here is the symbol of capacitor. There are a few symbols for different types of capacitor. So here is a typical one, which is a fixed capacitor, and this is a polarized capacitor. With the straight line represents the positive or the anode, and the curved one is the negative or the anode. We also have variable capacitor where we can change or vary the capacitance of the capacitor. And here is how capacitor look like physically. So we have one leg longer than the another leg, where similar with diode, the longer leg is the anode, the shorter leg is the cathode. A capacitor consists of two parallel metal plates which are separated by an insulator. So here is how it looks like. These two are the metal plates, and in between them is the insulator. The ability of a capacitor to store electrical charges is called capacitance with symbol C, and is measured in the unit farad F. The charge Q, or the quantity of electricity that can be stored in the electric field between the capacitor plates, is proportional to the applied voltage V and to the capacitance C of the capacitor. Hence, the formula of the capacitor is Q equals CV, where Q is the charge in unit coulombs C, C is the capacitance in unit farad F, and V is the voltage applied in unit volt V. Now, let's learn how to charge and discharge a capacitor. Let's look at this circuit. This capacitor is connected parallel to the light bulb and also parallel to a 6-volt battery. So this is the switch S1 and this is the switch S2. So when switch S1 is closed and switch S2 is open, here's how it looks like. The current flows into the capacitor, and the capacitor takes some time to be charged. So we can measure the potential difference across the capacitor Vc and plot the Vc time graph here. So the potential difference across the capacitor increases exponentially until when it reaches a time where the Vc equals to 6 volts, which is the same voltage as the battery. It will stop charging and maintain at this potential difference. So when the capacitor is charged until it reaches the same PD with the battery, then we open the switch S1 and close the switch S2. So let's see what will happen. So S1 is open and S2 is closed. Charges are released from capacitor, and current flows from the capacitor to the light bulb and turn on the light bulb. So here is the current flowing into the light bulb and turn on the light bulb, then return back to the capacitor. So now at this stage, the capacitor discharges to 0. Lastly, let's discuss resistors and their color codes. Resistors are usually used to control current in a circuit. Two parameters are considered when choosing a resistor, which are power rating and resistance value. Power rating of a resistor indicates the maximum rate of dissipation of electrical energy as heat before it is damaged. Examples are 0.25 watt and 1 watt. as you can see from this picture shows the physical look of fixed resistors. So each fixed resistors, there are 4 color bands. The value of resistance of a fixed resistor is shown by multicolor bands. And this table summarizes the color bands, the color code value, and the tolerance. So we start with the black. The color code value is 0. Brown, the color code is 1. Red is 2. Orange is 3. Yellow is 4. Green 5. Blue 6. Violet 7. Gray 8. And white 9. So some color bands represents tolerance as well. So the brown color is tolerance of plus minus 1%, red plus minus 2%, green plus minus 0.5%, blue plus minus 0.25%, violet plus minus 0.1%, gray plus minus 0.05%, and additional 2 colors which are gold plus minus 5% and silver plus minus 10%. So you need to remember all these color bands, their color code value and tolerance. So after you have memorized all the color bands, now the next question is how to read resistance value on a fixed resistor. So let's take a look of this picture. So there are 2 types of color bands. The first one is 5 bands and the second is the 4 bands. So for 5 bands, the first 3 color bands stand for the digit. The 4th color band is the number of zeros and the last color band stands for the tolerance. So for this case, yellow, the first band is yellow, which represents 4. The second color band is the violet, which stands for the 7. The third color band is 3, which is black, stand for 0. Orange stand for 3, and the tolerance band is the brown color, which is plus minus 1%. So for this case, the reading of the resistance is 4703, which means 470,000 or 470 kilo ohms. For the 4 bands, so the first 2 color bands stand for the digits. The third band is the number of zeros, and the last band is the tolerance. So for this case, blue is 6, gray is 8, and the red is 2. So the reading for this resistor is 682 or 6,800 ohms or 6.8 kilo ohms. The tolerance is gold, which is plus minus 5%. Now, the next question is, what are the color bands that represent fixed resistors of 582 plus minus 5% kilo ohms and 6.4 plus minus 10% kilo ohms? Let's see, 582 plus minus 5% kilo ohms is 582,000 plus minus percent ohms. We need to refer to the color codes here. So the 5 here is green, the 8 here is gray, and the 2 here is red. There are 3 zeros here, which is orange. So plus minus 5% is gold. So this is a 5 band color codes, which is gray, green, gray, red, orange, and gold. The next example is 6.4 kilo ohms plus minus 10% kilo ohms. So it is 6,400 plus minus 10% ohm. So 6 stand for blue, 4 stand for yellow. There are 2 zeros here, which is red. The tolerance 10%, which is silver. So the 4 band color codes is blue, yellow, red, and silver. Alright, that's all for this video. Thanks for watching, and I hope you enjoy it. Do you have any question or doubts to ask? Feel free to write it down in the comment area. I would love to hear from you. Do you like this video? Please don't forget to like it and share it with your friends. Alternatively, you can also enroll this full revision course at Udemy. At Udemy, you can track your learning more effectively. Download my notes in printable PDF form. Take a summative quiz at the end of each chapter. Get your first-hand updated contents from me. Get quicker response from me, and many more. You can get all these benefits at a very affordable price. It is one-time payment, no recurring fees, no hidden costs. This saves you thousands of dollars on expensive tuition fees and revision crash courses. And most importantly, your precious time. Finally, you can do your revision anytime you like, anywhere you prefer. All is available within your fingertips. Check out the description below this video and click on the enrollment link to register the course at discounted price. Alright, until then, see you in the next video. Have a great day ahead.